You know that feeling. Staring at a complex project, and you just know if you're off by like a tiny fraction of a millimeter.
Mm.
The whole thing's just scrap. Tasks that are slow, super wasteful, and need almost surgical precision. And for ages, older manufacturing methods, well, they've really limited what's possible, eaten into profits with every little mistake. So today, we're doing a deep dive into sheet metal cutting. And the sources you shared point to, well, a really transformative technology, a tool that's not just better, it fundamentally re-engineers how shops work. It's really changing the game in manufacturing.
That's absolutely right. Yeah. Our mission here is to unpack why the laser cutter isn't just, another machine on the floor, why it's being called the indispensable tool for sheet metal. We'll explore how it completely shifts the possibilities, saving material, time, money, pretty much on every single job. And this dive, I think, will uncover some pretty surprising things about precision manufacturing. It's fascinating stuff.
You really set that up well, that frustration when one tiny slip-up ruins everything.
Yeah.
And with sheet metal, you might think it's all about, brute force.
Yeah.
But the sources show it's more like surgery, right?
Yeah.
Can you break down why even a hair's breadth error is so, well, catastrophic, especially in those demanding industries?
Yeah, it's amazing how unforgiving the material actually is. You'd think, oh, a small error maybe doesn't matter much, but being off by just 0.1 millimeters, that can genuinely turn the entire piece into expensive scrap metal. Think about the cost there. And then you look at industries like, say, aerospace or high-end electronics.
Right.
Parts have to fit perfectly. Maybe it's for an aircraft wing structure or a complex circuit board housing. They demand specs with tolerances sometimes as tight as 0.003 to 0.006 millimeters.
Wow, that's incredibly small.
It is. Thinner than spider silk, practically. There's just zero margin for error. Absolutely none. And that extreme precision, it also means you need, well, incredibly sensitive process control. Every single variable, laser power, cutting speed, the exact focal position, it all has to be tuned perfectly for that specific metal, that thickness.
Yeah.
Like, get the angle wrong coming into a corner, just slightly,
Mm-hmm.
and you can get molten metal splashing back onto the cut edge. Ruins the finish instantly.
Ah, okay.
It's like a tiny, uncontrolled sort of detonation almost, where you need absolute control.
And it's not just the cut edge, is it? There's also that constant fight against the material warping or deforming, especially metals like aluminum, right? They expand a lot with heat. It seems like they just twist out of shape instantly.
Mm-hmm.
Without that perfect process, yeah, the part could just warp and be totally useless. Which brings up the big question, I guess, applying intense heat to metal. It just sounds like a recipe for warping.
Yeah.
Piles of scrap.
No.
So how on earth does a laser cutter manage to control that thermal distortion on sheet metal? It feels counterintuitive.
Well, it really comes down to the core mechanism. You've got this highly focused beam, and it moves incredibly fast. So the first key thing is that speed. The laser head itself moves across the metal at several meters to a minute.
Several meters per minute.
Yeah. So the heat goes on, and then it's gone so quickly that it just doesn't have time to soak into the rest of the sheet. The cut's made, laser moves on, and the surrounding metal doesn't really get hot enough to deform significantly.
So like a lightning-fast surgical strike. Almost no collateral damage.
Exactly. Yeah. Think of it like searing a steak, maybe. You want that perfect crust, fast heat, but you don't cook the whole thing through instantly.
Right. Good analogy.
The laser does that with metal. Perfect cut, minimal impact around it. And second, the beam itself is incredibly focused. All that energy is concentrated into a tiny, tiny spot, often just a fraction of a millimeter wide. This creates a very, very small heat-affected zone, the HAZ. And minimizing that HAZ is absolutely crucial for preventing warping.
Okay, the minimal HAZ.
Got it. And then finally, there are the assist gases. We use gases, often nitrogen, that blow the molten metal away and simultaneously cool the cut edge, like instantly. So for most sheet metal jobs, this pretty much makes distortion a non-issue. Now, okay, really thick materials, they can still be a challenge, right? Heat has more time to spread. But for your typical sheet metal work, it's remarkably effective. It's fundamentally changed how heat and metal interact in cutting. It basically eliminated what used to be a huge source of waste, those warped parts. That's the real breakthrough.
That's genuinely astonishing. How
Yeah.
they control the heat, turning that big challenge into, well, almost a non-issue for most jobs.
Yeah.
But that precision, it's not just about preventing problems, is it? It must unlock completely new design possibilities, too. How does the laser manage those really intricate patterns you see, like complex logos or super delicate grill designs?
Yeah, it's that Powerful mix, really.
Yeah.
The laser's ultra-precise beam, combined with very flexible CNC programming, CNC being computer numerical control, essentially. It's all driven by digital blueprints, CAD files.
Right.
This lets it cut basically any digital design you can create flawlessly. And the numbers, they really tell the story. You're talking positioning accuracy around plus or minus 0.05 millimeters, repeat accuracy of 0.02 millimeters. You can hit tolerances as fine as 0.00005 inches.
Wow.
And here's a really key part. The cutting kerf, that's the actual width of the cut itself, is typically only 0.1 to 0.2 millimeters wide.
Tiny.
Incredibly tiny. And that allows for those super sharp corners, unbelievable fine details, things impossible with older methods. Plus, the edges come out smooth, generally burr-free, which is critical for anything aesthetic, architectural panels, custom art.
That idea of from digital file to perfect part,
Yeah.
it sounds almost magical. Are there any common misconceptions or hidden challenges there, even with a laser?
That's a good point. It is incredibly seamless, but yeah, not quite magic. The biggest win is definitely the flexibility from the CNC. You take a CAD file, load it up, and you can be cutting in minutes, literally. No need for expensive physical molds or dies,
Yeah.
no tooling costs for new design. And because it's a non-contact process, you can cut just one prototype, see how it looks, then immediately switch to a totally different design file. It's absolutely perfect for rapid product development. Your design freedom isn't tied down by physical tooling anymore. The challenge, if there is one, is often just in the initial design file itself, making sure it's properly optimized to really leverage that laser precision.
Okay, so let's get right to it then. We've heard about what the laser can do, but why choose it over, say, the common alternatives,
Yeah.
like a punch press or a shear machine for sheet metal?
Yeah.
Let's maybe focus on a couple of key differences, like flexibility. You said the laser is almost unlimited. How does that really stack up against a punch press mold?
Yeah, that's a huge differentiator. With a punch press, you are completely locked into the shape of that physical tool, that mold. Want a new shape. Even a small tweak, you need a brand new mold. That takes time, and it's really expensive to make.
Right, significant cost.
Oh, yeah.
Yeah.
But with the laser, it's just uploading a different digital file. If you can draw it in CAD, the laser can cut it pretty much instantly. It's like custom tailoring versus only having off-the-rack sizes. And a shear, well, that can only cut straight lines, period.
Okay. And edge quality.
Yeah.
That seems critical too. I can't imagine a punch press, literally stamping through metal gives you that smooth laser finish.
You're absolutely spot on. A punch press, it violently stamps through the metal. It can be fast, yeah, especially for lots of simple identical holes. But that stamping action, it almost always leaves burrs and often causes some distortion right around the cut edge, too.
So extra finishing steps needed.
Frequently, yeah. Deburring adds time, adds cost. The laser, though, being non-contact, it melts or vaporizes the metal with that focused beam, so you get smooth, clean, burr-free edges right off the machine for almost any shape. That means way more flexibility and just a much better finish from the get-go. So look, traditional tools definitely still have their place, right, for certain simple high-volume jobs. But where edge quality really matters, or the designs are complex, or you need that digital flexibility, the laser is just superior.
Okay, so the core takeaway seems pretty clear. The laser cutter really is arguably the ultimate tool for modern sheet metal work. Its precision, its speed, that design flexibility, it just massively cuts down on a waste and cost in manufacturing.
Absolutely. It genuinely offers capabilities that are, well, superior to traditional cutting methods for today's fabrication challenges. For any shop that's looking to innovate, streamline their workflow, significantly expand what they can offer, a laser cutter isn't just nice to have, it's become pretty much a crucial piece of equipment.
Right. And just as we wrap up this deep dive, here's maybe a final thought to leave everyone with.
Yeah.
We talked a lot about efficiency, cost savings, precision, which is huge. But think about this. How do these kinds of tools with such extreme precision and flexibility, how do they fundamentally change the nature of design itself? Do they push the boundaries of what engineers, what artists can even imagine creating in the physical world, allowing them to sort of dream bigger than ever before?